Welcome back. As I mentioned before, short circuit impedance test is a test which we do in order to basically measure the losses in copper, a certain percentage. How do we execute the test? The secondary side is short-circuited. There are some cases when the test is done in a different way, but for these purposes, the secondary side is short-circuited. And in this case, I used 2 wires between phases. I could have used maybe 1, but the more wires you put, the better short-circuiting you do, the better will the result be. If you are doing this on a bigger transformer, I propose thick cables. The thicker, the better. So I short-circuited the secondary side, and now I'm going to generate AC voltage on the primary side. So phases A and B will be the first test. Let's do that. Right, so let's do a short circuit impedance test. Once again, power transformers. Once again, short circuit impedance. Not once again, first time short circuit impedance. If we are not sure how we need to connect, we press the question mark button and we see the connections. And basically that's what we have here. We will generate voltage from here. And so the voltage, let's say 100 volts, will be sent to an ammeter which will very accurately measure the current. And we will send that current through this wire onto the transformer. We can see that actually here. So connection and then going to the transformer. And we close the circuit with this wire here. And then in the same point where I'm sending the current, I need to measure the voltage drop. Since the name of the test is short circuit impedance, we need to short circuit the secondary side, and it's a good idea to use thicker wires. In my case, you will see what I used, and I have short circuited the secondary side. How do we execute the test? Again, we need to change the connections. First we do AB, then BC, then CA. If we have STS, we don't need to do that. STCS. But now, let me first do test number 1. AB. I'm connected between phases A and B on the primary side with the secondary side short-circuited. I'm going to generate 100 volt and 1 amp. Actually, as soon as one of these two conditions is reached, the device will not increase the voltage or the current. So let me add the test. I'm adding the test and pressing the button. The STS will run and it will automatically stop the generation, after which we will change the connections to B and C. Right now we generated 100 volts, actually 99.9. We measured this much current, 0.355, and now I need to change the connections. So having changed the connections, let me add now BC, add test, I press start. For the first 2 tests, don't expect to get any numbers. The numbers should come here, but you will get these numbers only when the 3rd test is executed. So the 2nd test is executed, we generated about 100 volts, and before the amount of current was 0.355, now it's 0.372. Let's go to the 3rd test, CA. I'm adding the test and I'm changing the connections. And I press start. What I expect is about 4%. That's the nominal value. And let's look at the last line. Actually, the nominal is 4% and we got 4.061, which is a good result. So I can also say evaluate test, pass, and now I have a good result for short circuit impedance. Right, we've done short circuit impedance test, but let me do now short circuit impedance with changed frequency. That means that we will repeat the short circuit impedance test. The connection is the same, but as you can see here, we will not do it at 50 Hertz. We will do it at 15, 30, 40, 75, 105, 220, 305, and 370. And now I'm connected between phases A and B. I am adding the test. It says that some voltages will be slightly modified. That's okay, fine with me. And I'm pressing start. What I'm seeing right now is essentially what we've done before, but at different frequencies. The result in the end will be 3 graphs. So actually 3 curves in one graph. And generally these curves should be the same. If they're not the same, it means there is a problem somewhere in the transformer and that too much magnetic field is, let's say, escaping from the core of the transformer. As I'm talking, I can see that only the 15 Hertz, the lowest frequency, is not able to generate up to 100 volts. We can see it here, it's 55, but that's fine, because we will use for all 3 phases the same frequencies. When this phase is done, I'm going to change from AB to BC and repeat this same test. So 305 is being done right now, 305 Hertz, and the last one will be 370 Hertz. All right, test is done. I'm moving on to phases BC. Adding the test. Once again, we'll get an alarm saying that at 15 Hertz it cannot generate 100, but it's fine. So BC. BC is done. Moving on to CA. Changing connections. And start. We can already see that the result is measured. We repeated the result from the past test. So 4.048, nominal value is 4. The maximum difference can be 2 to 3% depending on the type of the transformer. So we are well within the limits. It's actually 1% or maybe a little bit more than 1% difference, 1.2. So the test is done. We can see that we have repeated the previous result, 4.048, while the nominal value is 4. So we are well within the limits, which are 2 to 3%. And right now I have 1.2% difference, something like that. But how do we evaluate this result? We evaluate it by going here, pressing the button, and you can see now something which indicates an issue. Let me show you what is the issue. So we have 2 curves here, which more or less align with each other. They're, let's say, the same. But when I go B and C is different, which means there is something different within this transformer. Anyway, this is now the result for short circuit impedance test done in multiple frequency, whose name is frequency response to stray losses. And now we finish this test. Thank you.